All right, so Newton's method. This is section 3.8 in our book. So we jump from 3.6 to 3.8. So Newton's method is a way of approximating the zeros of a function on an interval. And you would need something like this when your calculator finds the zeros of a function. You have a graph and you have to mark a left side and a right side and a guess. It's using something like Newton's method, some kind of iterative process to find the zeros. And it's Newton's method is one way. Newton's method is nice because when it converges very quickly on the zero, and we'll talk about some of the things that you can prove about Newton's method once we talk about the process. So what we need for Newton's method is we have a function f, and our function needs to be continuous on some interval, some closed interval, and we need a differentiable on the open interval. And we need to know that it has a zero in that interval. So we've done some analysis. We've figured out that we have some function in this interval. It has our function has a zero at c. So f of c is 0. So what we're doing with Newton's method is we're approximating the zero by finding the zero of the tangent line. So what other application, what other thing that you can think of that you've talked about before do you approximate a function with its tangent line? Euler's method? Anything else? Anybody think of anything else where we approximate a function with some other function? Linear approximation. They're polynomials.
I know, but there's a word for it.
And there's a name, the guy that they're named after. What is it? Power series. Taylor polynomials, right? One of the first terms in a Taylor polynomial is can be a linear function. So we're Taylor polynomials. We add higher degree polynomials with Taylor polynomials to get a better approximation. But Newton's method, we're doing repeated approximations with the tangent line. So we're going to approximate the zero. We're going to guess at what the zero is of our function. So we have to start Newton's method with an initial guess. So we're going to say that equals x1. That's our first guess, x1. So let's draw a picture of what we're talking about here. Let me switch pages and we'll draw a picture. So we have, here are our axes. And we have some function here, like so. And here's our interval. This is going to be A, and B is over here somewhere. Because we have to have our zero in our interval. And here's C. We know we have a 0 in here somewhere. Now we're going to draw in, we're going to make an initial guess at, let's say our initial guess here, this is x1. We're going to guess that x1 is the 0. It's close to our 0. And we're going to construct the tangent line to f at x1. So let's draw in the tangent line here. And so here's our tangent line. It's not perfect, but you get the idea. And I'm saying it's tangent here, so that's a big point there. So this is our tangent line at x1. And we're going to write an equation for the tangent line, and we're going to use this x2, where the 0 of the tangent line, we're going to use that as our new estimate for the 0 of the function. And usually that 0 of the tangent line is a better estimate for the 0 of the function. So we're going to call this x2. So our intercept for the tangent line is x2, and this is usually a better approximation of the 0. So we guess x1, we are going to construct the equation, come up with the equation of the tangent line, and figure out how to come up with a value for x2. And then we're going to repeat that process. Then we're going to construct the tangent line. I'm not going to draw it in quite as nicely here. I'll do this one in blue. We're going to construct the tangent line at x2 and find the intercept of that tangent line, like so. And that's going to be our third approximation of the 0. And if our function behaves nicely and we come up with a good initial guess, this is going to quickly converge. The sequence x1, x2, x3 is going to quickly converge on this 0, C. And you can kind of convince yourself, if you sketched in the tangent line at x3, you're going to be closer to the 0, sketch in another tangent line, and you're just kind of finding these intercepts, and they quickly converge on the 0 of this function, if our function is behaving nicely. So let's write an equation for this tangent line. We're going to calculate x2. So up here at our initial guess, this point is at x1, f of x1. And here our point is x2, 0. That's this point here. So let's make the equation of this tangent line. And the slope of the tangent line is f prime at x1. So that's the slope of this red tangent line, is f prime of x1. And we have these points. So we're going to use point slope form, come up with an equation for the line. So y minus f of x1 equals f prime of x1 times x minus x1. And we're going to plug in this point, x2, 0. We end up with 0 equals f prime of x1 times x2 minus x1 plus f of x1. So I just substituted in this point, x2, 0, into this equation and rearranged a little bit. We solve for x2. So x2 equals x1 minus f of x1 over f prime of x1. And this is our new estimate for the 0 of our function. This is x2. And then we repeat this process. To find x3, we're going to say that x3 is x2 minus f of x2 over f prime of x2. And we can repeat this process as many times as we want until we get the desired accuracy. So I'm just going to write our next step. We would say that x3 is x2 minus f of x2 over f prime of x2. And if we needed an x4, we would do another iteration, x5, another iteration, and until we got the accuracy that we wanted. Does this make sense? This method pretty easy, pretty straightforward. It can get tedious calculating the derivatives and the values of the functions. If you have a complicated function, plugging in values for x and evaluating the function, evaluating the derivative, it can get a little tedious, but you have calculators. Yes.
Can we just use that general formula, or are we going to have to start from the beginning? Find x2.
Oh no.
Or can we just start with x2 equals x1 minus?
Oh yeah, no, you don't have to start with this.
Okay.
This is Newton's method.
Okay.
If we generalized it, we would say the way often you see it written is x sub, I'll say x of n is x of n minus 1 minus f of x n minus 1 over f prime x n minus 1. So we just have this recursive formula for our zeros. We always have to start with an initial guess. We have to start with some initial guess for our 0. How might we get our guess for our 0 of our function?
Somewhere in the interval?
Somewhere in the interval. So if we know, sometimes you'll be able to look at the function and say, okay, it's negative here, it's positive here. So somewhere in that interval, we're going to have a 0. You might have to graph it. You might have to do something. Sometimes the problems will give you an initial estimate. Use an initial estimate of x equals 2 and do this analysis. But you need to start with an initial estimate. You get a new estimate, then you plug that one into your formula. Do the process again.
How do you know when to stop?
It depends on the accuracy that you want. I think in the book, a lot of times the problems say until 2 successive estimates differ by 0.001 or something like that. And that'll tell you when to stop. Usually it goes very quickly. Newton's method tends to converge very quickly. So usually you don't have to do more than three iterations, maybe 4.
I'm guessing unless you're very far off the actual 0.
If you're far off from the actual 0, then you might have to go over and over and over and over again. Yeah, if your initial estimate is bad. And sometimes the problem will say use 3 iterations of Newton's method to approximate the 0 of this function. So let me write down any questions about the idea of Newton's method. Let me write down the steps just so you know how to go about if we're using when you do Newton's method. So we know that we have a 0 on some interval, and f is differentiable. If f fails to be differentiable anywhere on the interval, when you hit that point, then you run into a problem with Newton's method. You end up, if f is not differentiable, you can end up with trying to divide by 0, something like that. So f has to be differentiable. So you need to make an initial estimate. I'm going to say close to C. So close is a relative term. To make an initial estimate. 2, you make a new approximation using Newton's method. And then you repeat, and I'm not going to write down your formula again, we already wrote it down. And then repeat as often as necessary. So we have a nice algorithm for Newton's method. And it can be proven. We're not going to prove it in here, but it can be proven that if the sequence of the exabands, the sequence of our approximations, x1, x2, x3, if they converge to a limit, then that limit must be the zero of the function. So if our sequence of approximations converges, it must converge to the zero of the function. And we generally double the accuracy of our estimates with each iteration. So Newton's method is, like I said, it's very quick. Usually you double your accuracy. Newton's method is going to fail if f prime is 0 for any of our exabands in the interval, because we're dividing by f prime of exaban in Newton's method. So go back here. If we end up with a 0 derivative anywhere in our interval, then Newton's method fails. When that happens, you might have to make a new estimate. Because if you have a graph, just going to do a quick sketch here. If you have something like this and your zeros here, and you make your initial estimate over here, at some point as you're going through the process, you're going to get this for your tangent line, and then you get an f prime of that particular point of 0, and then you got a problem. So then you need to work a little harder to make a better initial estimate. Questions on that? All right. How much time do we have? Let's look at a quick example of using Newton's method, and then hopefully I can get to my demonstration. But we might run out of time. Yes.
Why is it not converge to 0?
Good question. I should have made my graph, for the purpose of my illustration, I should have made the graph look like this. Okay? All right. Example. So we have f of x equals x cubed minus 2x minus 5 equals 0. And we want to approximate with 3 iterations. And we start with x1 equals 2. We can come up with this initial estimate if we look, because we have a nice polynomial here. If we plug in some values, we can see, if we plug in 1, we see f of 1 is negative 6, f of 2 is negative 1, and f of 3 is 16. So we know that our estimate has to be somewhere somewhere between 2 and 3. So we're going to start with an initial estimate of 2. That's how I came up with this initial estimate. So let's start out. So f prime is 3x squared minus 2. And I'm going to plug this into Newton's method. So we know that x2 equals, and let me write out the steps. So x sub n plus 1 equals x sub n, and I use a different subscript here, but that's okay. X sub n cubed minus 2x sub n minus 5 over 3x sub n minus 2. So my second estimate, x sub 2, is x sub n, x sub 1 is 2, so I'm plugging that in here. 2 minus 2 cubed minus 2 times 2. I'm just plugging in 2 for my x sub n minus 5 all over 3 times 2 minus 2. If I calculate that all out, that's about 2.1. And then for my third iteration, for x sub 3, I just plug in 2.1 in here. So x sub 3 is going to be 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5 over 3 times 2.1. 2.1, this should be 2.1 cubed.
Mr. Beamer, on the bottom,
Yes.
should be 3 times 2 squared.
Oh, 2 squared? Did I make a... Forgot this. This should be squared. Oh, there we go. Okay. And this doesn't come out to 2.1? 1.9. Thank you. What is it? It is 2.1, so I just forgot to write the square. I just forgot to write the square there. And this should be 2.1 squared. And this comes out to about 2.0946. And if we did another iteration, our fourth iteration would be almost exactly the same as this. 2.0. It would be different. It would differ even further out here. So. I guess so. We started our initial estimate. So this would be 1, 2. So I did 2 iterations. If I did the third iteration with 2.0946, my third iteration would come out 2.0946, and it would differ even further out. So I just didn't go through the process. So that's all there is to Newton's method. Where it gets tedious is calculating these things, because you end up with plugging in long decimals into your expression. Yes. Yes. So the problem asks for 3. I didn't do the third one. The third one is the same, and you end up with a number that's almost exactly the same.
Did you capture it up the very first, if it X within Q?
No. I just to remind us what we were doing, what our function was, what we're plugging in. But you don't have to do that. You could jump right in with this. And I should have paid more attention because I forgot my squares there. Questions? All right. Newton's method, again, more derivatives, more algebra, but pretty straightforward algorithm. Let me show you. We have a few minutes. 17. Okay, good. This is where Newton's method, I think, is really interesting. Newton's method leads to. Let me back up a little bit. I really like it when math leads to really unexpected results. So this seems very straightforward. Do this algorithm, kind of plug and chug. But Newton's method can lead to chaos. And what I mean by that is, and I'm going to do this really quickly because I think this is really cool. If we have this function, this is one example. We have a function y equals 4x to the fourth minus 4x squared. This function looks something like, and I'm doing this very quickly, this is not, you're not going to need to know this, I just find this very fascinating. The function looks something like this. So it looks like this, and we have a root here. I'm going to call this root A, this root B, and this root C. And over here, we have minus square root of 2 over 2. And we have minus square root of 21 over 7. And over here we have the positives of those. Square root of 21 over 7 and square root of 2 over 2.
You didn't take a number within like root 2 over 2 or wherever the absolute minimum are, wouldn't it end up leading to nowhere? It would never come back forth with that.
So that's part of what happens, but it's even more interesting than that. In infinitely many open subintervals between negative square root of 2 over 2 and square root of 27 over 7, infinitely many open subintervals, you can get Newton's method leads to root A, alternating with infinitely many open subintervals that lead to root B. So if you change your initial guess by the tiniest amount, you end up Newton's method leads to a different root. Between these two, you end up with infinitely many open subintervals that, between these two, you end up with alternating between root B and C, infinitely many open subintervals. So you can subdivide that subinterval as many times as you want, and you move a tiny bit, and your estimate is going to go to a different root. And that's why they call it chaos, because a change in the initial condition, a tiny change, leads to a dramatically different result. And you can subdivide that open subinterval infinitely many times, and if you move the tiniest amount, you're going to go to a different root. So you never get a stable thing with Newton's method. If we're over here greater than square root of 2 over 2, we get to root C, and if we're less than negative square root of 2 over 2, we get to root A. But in here, if we make a tiny shift in our initial estimate, we end up leading to different roots. And at the boundaries of the intervals, the Newton's method does not converge. So at the boundaries, Newton's method doesn't converge. So that's a really interesting result. Now, I just wanted to point this out, and I have a demonstration here that I want to show you that kind of illustrates this with a complex. Now I can't get to my my folder here. Let me do this really quickly. Are we almost out of time? We are. I'll show the demonstration on Tuesday. So let me get you your homework. Is it page 233? Yeah. Thank you. There you go.